how to use this. Okay. Okay. Mm-hmm. Can you see? Okay. Thank you very much, Chairman. First of all, I'd like to thank organizers for us, to be here. Wonderful location. This is, in fact, the third time, to come to Brazil. And last time I was across here, it was Recife. And so I could expect what kind of weather here quite well. By the way, today I'm going to show you about Terahertz emission from a high temperature superconductor 212 mesa structures, especially in a higher symmetry mesa. This has somewhat special properties. That is what I wanted to say to you. However, because perhaps you know, all of you know already, Professor Abrikosov has passed away at the end of March this year. And I think I have very special photos for him when he came to Japan about 13, 14 years ago. After Nobel Prize he got, I invited him to Japan because he said, I have never been to Japan, and I wanted to see people who has carried out some field theoretic work for superconductivity at the early beginning of the 50s or so. So I invited him to come to Japan, and that is, so if you allow me to show some, maybe several pictures before my talk, I think it's okay. Here, this is a picture. Our university gave him honorarium doctor title for him. This is the ceremony for that. This is the so Abrikosov and myself, and this is our president of university, and he got this title, and he made a address, speech. And he mentioned in his talk, I have never had occasion such sort of many people in my talk. And it was very impressive what he said. In addition to him, in the talk, we invited other speakers. This is still Abrikosov, Dr. Tonomura, and he has also passed away several years ago. And you know him? He is not around here in this conference. You know him? Professor Tachiki? He is not here also. And this is Professor Tanaka, Shoji Tanaka. He also passed away a few years ago. Yeah, you know this gentleman. And this is a meeting in the president room. This is the president of our university. And we are just chatting with him. By the way, he came to Japan with his daughter. Okay, I have I have many figures, maybe thousands of pictures. He stayed about 1 week in Japan, and he made a trip from Tsukuba to Tokyo, Kyoto, Sendai, and came back to Tsukuba in in a week. So I took also 1,000 pictures, so that if you like to have it, please come to me. I can give you. Come back to my talk. This is my outline of talk. I just give you a brief introduction of Terahertz principle, mainly. Maybe most of you know, but and I like to come to directly to hear effect of the shape of on the terahertz emission, and especially triangular square. Maybe square is most symmetric case. We are now trying to make annular mesa, but never success, so that I don't go into the conclusion. By the way, at the last, I'll show you some of our attempt to make this device for commercialization. Okay, so this is the essence of terahertz radiation. A visco crystal, as we can grow such a large crystal, and I hope, I think we can make one of the best crystals in the world. And of course, this atomically arranged in such a way, superconducting copper oxide layer, double layer, inserted this normal part of material, bismuth 2O2 layers, and this makes intrinsic Josephson junction. So this is stacked along c-axis, and this distance is about 15 angstroms, so that this is really atomic scale of Josephson junction stacked along the c-axis. So 1 micron thick device has about 670 layers of Josephson junctions. And if you apply DC current through this junction, then we have AC Josephson effect, which makes resonance synchronized, and we get coherent radiation from this device. So it is nothing but, this is just the AC Josephson effect, the schematic pictorial way. This, oops, sorry. Oh, sorry. This Cooper pair can go back and forth by putting DC voltage in between two superconductors. And then this Cooper pair just generate this AC radiation with this relation. So this is Josephson effect. This is nothing but the emission from just, atom. In atom, we have two different energy state, and in proportional to this energy difference, we get the photon, emission from there. It is exactly the same, but we can tune this continuously, but here we cannot tune because the atomic orbit is just discrete in energy. This is just the experimental way how to make this device. So this is the frequency diagram with the power, conventional and also IJJ we call devices, present status. And most of device sharply drops in the power as frequency goes above 1 terahertz especially. So between 1 terahertz to maybe few terahertz, there is a very sharp gap in which we cannot produce electromagnetic wave. So this is we call terahertz gap. Even now, it is very difficult. But IJJ, our device can can fill this gap very well, so that we are now trying to make higher power and also higher frequency device. By the way, this was discovered about just 10 years ago. This is just a picture, and this is the first paper written by Ludwig. He is not here, but this is our group, and this is Argon group in a collaboration with Argon group, of course. This is the, at that time, this Guelph came to us, and we are trying to measure the spectrum from Mesas. He brought Mesa, a few Mesas, and we are trying to, this is the cluster, and we are just thinking, discussing what is this, and so on, so on. And this is the first. It was June in 2007. Of course, this Josephson radiation is interpreted in such a way. This is just the AC Josephson effect, and those superconducting layers emit photon, each of them, but it becomes synchronized so that it has coherent radiation. So that if we have number of layers, power goes to squared number of layers. That means if we have 1,000 layers in material, we get 10 to the 6 times power. That is gigantic enhancement. So that's what we get very large power from that. However, there has been lots of problems for that. It has to be solved. So we have been working on that problem several years, and finally we came to this way how to make better emitters. This is we call standalone mesa. Standalone mesa means we just cut off small part of superconductor with something like micron thick, and we just glue on the sapphire plate in this case, so that just this is standing alone without any other superconducting part. So we just pass current, DC current, from top to bottom or other way around, and then we get very large and very sharp spectrum like that. This is not spectrum, but very sharp radiation pattern. So this, peak intensity is very sharp. Although total power maybe not after integration. However, we tried to make many different shapes because the radiation can come from different kind of shapes. We started from this rectangular mesa, but in fact it's not limited to a rectangular. We can do square, cylindrical discs, triangular or isosceles triangular, many things. I think in fact any kind of shape, if you have resonance, we can make radiation. However, of course, the eigenfrequency from this, there is eigenfrequency associated with the shape, so that shape is important for determining the frequencies. It is written here. In the case of rectangular shape, it is very simple, like a quantum mechanical, box, two-dimensional quantum mechanical box, so that this length and this width give rise to such sort of relation for frequencies. So we tested this, whether this really working or not, by changing W and L in such a way, and in fact it really worked very well. And also we can predict what kind of radiation pattern we get, assuming this parallel plate model. However, we have to take into account the superconducting electron in addition to that, because in this model, this is just nothing but antenna, parallel plate antenna, without any superconducting electrons. So that for superconductors, we have to add some effect from superconducting electron. Anyway, using this technique, this is already established way how to calculate it. So you can predict the radiation pattern from particular shape of mesa. So for instance, for such a rectangular standalone mesa, we'll give you such sort of pattern. This is we call TM10 mode. and the higher harmonic, second higher harmonic, give this TM to 0 modes like that. So if we measure